In this video, I'd like to go through the steps required to configure an STM32H7 microcontroller to use its built-in analog to digital converters, or ADCs for short. Several of these ADC channels triggered by a conversion timer running at a fixed sampling rate, so we're going to use an internal hardware timer from the STM32 to trigger the conversions, and we would like to offload the transfer from our measurements from the ADCs to the required memory locations via the use of DMA, so that can effectively run in the background. Using ADCs is very common in many embedded systems. The board we'll be running this on and we'll be writing software for, we can see here. On the left hand side we have the main board, so to speak, which is effectively an audio processing platform based on an STM32H7 microcontroller. This has various peripherals connected to it, ADCs, DACs, LEDs and so on, but also because we'd like to control this board, we want to change, for example, various filter settings, parameters of the effects that we're running on this audio DSP board. I'm running several ADC channels from this STM32H7 microcontroller through to a ribbon connector or FFC connector, which then connects to the right hand side to a different board which effectively just has 5 potentiometers on it. We can apply voltage across these potentiometers and read out the voltage at the wiper terminal depending on the rotation of these potentiometers, and that's what we'd like to read into the ADC. We can use that to vary parameters and the effects on the system running on the left-hand side. The reason that I'm connecting these via ribbon cable and ribbon connectors is that these boards sit at different heights in an enclosure. If you'd like to see this board in action, I'd recommend watching video number 117 on my channel, where these two boards are actually built into this guitar pedal enclosure, and we go through a DSP overdrive algorithm in software, also running on the STM32H7. The parameters of that particular algorithm are controlled by these potentiometers, which are read in the background, so to speak, via ADC, a sampling timer, and we help offload the CPU by using DMA. So I'd like to show you how I set that up. In particular for the STM32H7 microcontroller, there are some quirks, especially when we start enabling the caches that are available in the H7 series of microcontrollers, because that, in combination with DMA, can cause some issues which we need to circumvent. Also, to show you a different example, at the end I'd like to show you what quirks there are when using STM32U5 microcontrollers, which I'm using, for example, for this micro quadcopter control PCB, because for this ultra-low power device, there are some quirks when setting up the ADCs that we need to pay attention to, and we'll go over those things briefly at the end of this video. A huge thank you to PCBWay for sponsoring this video. All the PCBs you're seeing in this video and we saw at the start of this video were manufactured and assembled by PCBWay in China. For this, I used their PCB prototype service as well as their PCB assembly service. I'd strongly suggest checking them out for yourself, and I'll leave links to them in the description box below. Make sure also to follow PCBWay on Instagram to see all the cool designs that they are producing, as well as various contests they run throughout the year, and occasionally you'll see some of my designs pop up there as well. Before we jump over to the schematics, here's a simplified diagram of what's going on in this particular audio DSP project with the ADC connections. We have our system digital logic voltage, which is VDD. Typically for a microcontroller that might be something like 3.3 volts, could of course be lower or higher. That's being fed through a potentiometer, and the other side of the potentiometer is grounded. We take the middle connection, or the wiper connection of the potentiometer, and feed that to our ADC. Now we could feed that to the ADC directly, but I would strongly suggest always at least putting a placeholder low-pass filter in place, because there will be noise superimposed, for example, on the supply, or there might be external noise coming into the lines, so I typically always place some sort of filter before I go into an ADC. That's a topic for an entire new video, is how to create ADC front ends. But in any case, we have our potential divider, so to speak, our potentiometer, feeding through a low-pass filter to try and take away some of that excess high-frequency noise, and then we feed that to the built-in ADCs of the STM32H7 microcontroller. So our potentiometers are located on the board we saw in the picture previously. There's nothing else on this board other than the potentiometers and a ribbon connector, so we connect this up to the carrier board. On the carrier board then we connect up our ribbon cable to this ribbon connector, and as we can see here then we have these RC low pass filters which then feed into the STM32H7 pins that are hooked up to the ADC channels. The actual schematic is then shown here. We have our ribbon connector. I am filtering the supply voltage that's going to the potentiometers, so we're 3.3 volts. We have a very basic pi filter feeding the 3.3 volts that then gets fed to the potentiometers. The output, so to speak, from the potentiometers are these control signals. I'm only using 5 for this particular board and project. These are then low pass filtered and have a cutoff frequency of about 310 Hz with a 5.1K resistor and 100 nanofarad capacitor, and then those feed to the ADC channels of the STM32 microcontroller. The particular STM32 microcontroller I'm using here is an H7B0VBT6, and I'm using the first few channels of that, as we can see here. In terms of supplies, of course, we have 3.3 volts going to our digital logic, and we also have the VDDA and VREF pins that are then also externally filtered because these are the supply pins for the STM32H7's ADC. Now, there's not particularly much or heavy filtering going on. We simply want to read potentiometer values. Very low noise or particularly high accuracy for this application is not required, but keep that in mind for your application that you might need more or less filtering. We won't be going into much depth into this video other than setting up STM32Cube IDE, our project, writing the code, and then of course going through a live demo of what's going on and looking at the quirks of the H7 and U5 microcontrollers. I'd strongly suggest, if you're interested, reading through application note AN2834 by ST on how to optimize the ADC accuracy in the STM32 MCUs. This is quite a lengthy document, but very, very interesting, and shows you the pitfalls of using particular types of ADCs, how to achieve the best accuracy, how to design the interfaces to the ADC, and more. They talk about compensation, various errors, and how to reduce those errors in the readings, how to optimize the ADC accuracy, and looking at various different effects, and also talking about how these ADCs work in part. Within that application note, and just briefly to cover this, we can see, for example, typical application schematics before an ADC input, and we can also see the low-pass filter here, but we can also see that there are some problems and things we need to watch out for when choosing our input or source resistances and any external capacitances attached to the ADC inputs. So please make sure to read through this if you're implementing this in your own design. Keep in mind also, on the topic of maximum source impedances and so on, please make sure to check out the datasheet of the relevant microcontroller. I'm using an STM32H7B0VBT6, and looking at the datasheet, looking at the ADC characteristics, this happens to be a 16-bit maximum ADC. We can see the various specifications, so supply voltages, clock frequencies this ADC can run at, sampling rates, and so on. But also, if we look at the resistance AIN, so the maximum external input impedance, depending on what resolution we want, we are only allowed a specific source impedance connected to our ADC input pins. So you might need some buffering to lower that source impedance if you're trying to get the maximum resolution out of your ADC. For us, we don't really need 16 bits, and we're just reading potentiometers, so accuracy and speed in this particular example aren't particularly of importance, but do keep this in mind and make sure to read those app notes and datasheets. Lastly, before we get started, I'll leave this link in the description box below as well. Make sure to check out the page Getting Started with ADCs on the ST Microelectronics wiki page, and this goes through the structure of an ADC, what the various terminologies mean, and what various conversion modes we have in there as well. If you would like to follow along, make sure to download STM32Cube IDE, which is a free development environment, which is my favorite way to develop for these STM32 microcontrollers. I'll leave a link to this in the description box below. In Cube IDE, I've started a new project, and I'll enter the part number for my MCU, and give your project a name, and you can leave everything else as a default and click Finish. For now, we won't apply the default memory protection unit configuration for this H7, so let's click on No, but we will need to come back to that later on when we enable caches. If you're new to this, the configuration can seem quite daunting because there's quite a few peripherals we have to configure, and per peripheral there are many different options and settings we need to configure, and oftentimes their meaning, at least in Cube IDE, isn't directly obvious. The first thing I typically do is enable my debug lines and a crystal oscillator if I'm using an external one. For the sake of demonstration, I'll just be using the internal crystal oscillator, but I would like to, of course, enable serial wire debug, which is my main programming interface. So I can go to Trace and Debug, click on Debug on the left, then drop down and choose serial wire. And this then enables the programming interface on the top right of the MCU. Again, we will be using the internal crystal, and we'll get to the clock configuration later on. The next thing we want to enable is, if we go to left side analog, then ADC1, we want to enable the relevant ADC channels, and you can see there's quite a few here. Jumping back to Altium Designer to look at the schematic, for us, I'm only actually using the first 5 ADC channels, but for the sake of time, we're just going to enable 3, and you can see control 1, 2, 3 are fed to ADC1 in 16, in 17, and in 14. So these are the channels I would like to enable. So we have 16 on the left-hand side. This is a single-ended measurement. Of course, you could go with differential, but for pots, we don't really need that. So we'll go with single-ended, 16, 17, and 14. we can immediately see, typically for ADCs, we only have one pin that is mapped per ADC channel. So we can't, for example, move in P16 to a different channel usually, and they are usually quite fixed. But here we see we have PA0, PA1, and PA2 now enabled, and these are the first 3 potentiometers, for example, in my design. With these channels now enabled, I can go to parameter settings, and here we can see there's lots and lots of things to configure, but we only need a few of them. First of all, clock prescaler determines how fast the sampling clock of the ADC is. If we jump over to the clock configuration panel and scroll down, and this depends on what MCU you're using, we can see there's a specific ADC clock that gets fed to the ADC. In this case, this isn't configured correctly, and we'll do that later on. But that core clock can get divided down by this clock prescaler. So it can be divided by 2, 4, 6, 8, and so on, and we'll just keep it at 2 for now. This really gets more important if you want to do very, very high frequency measurements. For us, we're probably only going to sample maybe 10, 100 times per second, but keep that in mind if you're doing high frequency measurements. Resolution is how many bits we have for the measurement, so we'll keep that at 16 bits. For our pots, we don't really need that. We could go down to 8 or 12 bits, but we'll just stick with 16 bits for simplicity. But keep in mind, the actual equivalent number of bits for the microcontroller depends on various different factors, such as interface, sampling speeds, voltages, and so on. Next, we have scan conversion mode. Scan conversion mode means we are just sampling more than one channel. You can see here, we can't actually enable scan conversion mode. What we have to do first is go down to the conversion section of the ADC and change the number of conversions to more than one. In our case, we have 3 channels, so we want 3 conversions. So if I change that to 3 and then go up again, now scan conversion mode is enabled. There are other parameters such as continuous, discontinuous conversion mode, but those are typically used if you're not using DMA. Then we have end of conversion selection, and we want our end of conversion trigger, so to speak, be when all of the conversions are complete for all of our channels, in this case 3. So I'll select that. We'll come back to some of these other settings later after we've configured the DMA. Scrolling back down again, we have regular conversions enabled, 3 conversions enabled for our 3 channels, and then we also have the conversion source. Now we could either trigger the conversions or tell the ADC to sample by a software command, but there are also various other commands such as timers we could use. And for timers, typically want a trigger out event is the simplest, and I'll just choose a random timer. Let's just choose time 8, trigger out event. Every time this timer, in our case timer 8, sends an update event, the ADC will begin sampling these 3 channels. So therefore, later on, we will see that we can configure the timer to pulse at a certain rate, so a certain number of times per second, which means we get a certain number of samples per second. Trigger detection, typically just rising edge. And now we have these various ranks. Ranks are in which order the ADC samples the data. So we have 3 channels. Which ones get sampled first, second, and then third? We could do 16, 17, 14, but we could also do 14, 16, 17, and any permutation of those. If we expand the rank section, we can see we can choose the channel, we can choose the sampling time, and some things to do with offset. For us, we want to do channel 16, 17, and 14 in that order because that's potentiometer 1, 2, and 3 in this example. So channel 16 is okay for the first rank, and then we have the sampling time. The sampling time is given in cycles, and the cycles depend, again, on the clock configuration, the ADC frequency we have, as well as the clock prescaler. And those are the actual cycles this is talking about in this section. Now, if you want very, very fast conversions, we may sacrifice accuracy for that. So typically, unless you are particularly time pressed, simply speaking, we want to have a higher sampling time, so more cycles per sample, to improve the accuracy for this particular type of ADC. Because we're reading at a very, very slow rate, we only want to look at potentiometer values, which are human controlled, so we only need maybe a sampling rate of 10 to 100 Hertz. So therefore, let's go with a sampling time of something rather high in this list, so around 400 cycles. Let's open rank 2. We want channel 17 next, so let's choose channel 17 and we'll choose the same sampling time. Then rank 3, the third channel, is channel 14 and we'll change the sampling time to the same as the others. Now there are many, many other parameters that you can configure depending on your situation, but these are kind of the bare minimum for the ADC parameters. Within the ADC, this is almost everything we need to configure, but we do want to set up, if we go to the NVIC settings, that we enable interrupts, and then we go to the DMA settings to enable the DMA. If we don't use DMA, we have to do polling conversion or interrupt conversion, which could put a higher load on the CPU to trigger the measurements, to read back the data, put that in memory. We can just do that with DMA. So in the background, once the conversions are complete, the DMA will access the peripheral, the ADC in this case, take the measurements and put them into a specific memory location we determine. And that can run with pretty much minimal CPU intervention. So in DMA settings, let's click on Add. DMA request is ADC1, keep the DMA stream as default, and the direction is, of course, peripheral to memory from the ADC to a specific memory location, and for now, the priority is low. That depends on different DMA streams you might have in your designs, but comparatively for us, our priority is low because these are just potentiometer measurements. The data width is half word for peripheral and for memory. Remember our parameter settings, we had that we want a 16-bit resolution, a word is 32 bits, so we need half a word, which is 16 bits. We will change the mode of the DMA to circular. We won't want to have to restart the DMA the whole time. After these ADC measurements have been put into memory, we want the DMA to continuously do this, so to speak, in the background every time conversions are complete. Then, jumping back to parameter settings, previously we had this conversion data management mode in the ADC settings. We want to change that to DMA circular mode. So we link the ADC with the DMA. So quite quickly we've set up our ADC and the DMA, but remember we also selected the external trigger to be timer 8 trigger out event. And we have to set up timer 8 because that'll be, in our case, the conversion timer. So let's on the left hand side go to timer 8, and choose the clock source to be internal clock. And this will then enable all these counter settings and trigger settings at the bottom. Now we want to set up our timer in a way that we get a specified sampling frequency or sampling rate. For example, our potentiometers, we might want to sample at 10 Hertz, so we need to set up our timer that we get a timer frequency of 10 times per second. We have the prescaler to do this, and we have the auto reload register or the counter period to do this. These prescalers and counter periods divide down the effective frequency of this timer. But the question is, what is the core frequency of this timer? To do that, let's go to the clock configuration tab. On the right-hand side, we can see we have various links from our clock configuration and our clock sources through the PLLs to various peripherals and timers. We have them to the CPU clocks, peripheral clocks, we have some timer clocks here, and so on. And the actual timer clock will be our core frequency. To see what timer core clock is being fed how, we can go to the STM32 datasheet of the relevant part. So for example, the part I'm using here, the H7 part, looking at page 10, we can see the block diagram. If we're using timer 8, we can see this on the bottom left-hand side. Timer 8 is connected to the APB2 clock. So back in Cube IDE, we can see 64 with these default settings is our core clock for the timer. Now keep in mind, none of this clock configuration is configured yet. This depends on other peripherals you have. It depends on if you're using the high-speed external crystal, if you're using internal crystals, and so on. For us, we're just using the internal crystals, and I'd like a core frequency of 280 megahertz, and then I can click enter and OK, and it'll try and find a solution for all the PLLs to get appropriate values. And there we go. Now it's adjusted the PLL values to give us a core frequency of 280 megahertz, which is the maximum for this device. If we scroll down, we can see now by default it's set up the ADC to have about a 43 megahertz clock, but we can change that depending on our needs. For us, it doesn't really matter. What does matter in our case is knowing what the APB2 timer clock source is, and this happens to be 280 megahertz. Now 280 megahertz is our core clock frequency. To then actually configure the timer to have a specific sampling frequency or update frequency, we simply use then the timer clock. In our case, this was 280 megahertz. The update frequency is then the 280 megahertz divided by the prescaler plus 1 divided by the counter period plus 1. So keep in mind these plus ones that get added to the prescaler and the period. So with a core clock frequency of 280 megahertz, so 280 times 10 to the 6, we need to use the prescaler and auto reload register or counter period to divide this down to an appropriate sampling frequency for our ADCs. I want to have something like 10 Hertz. Keep in mind the prescaler in this case is a 16-bit maximum value and the counter period in this case is a maximum 16-bit value. So we're limited by a decimal number of 2 to the 16 minus 1. So let's say if we divide 280 megahertz divided by 28,000, we get 10,000 as our frequency. And if we divide that again by 1,000, we get an output frequency of our timer of 10 Hertz. So 280 megahertz divided by 28,000 divided by 1,000 gives us 10 Hertz. So that's what I'm going to enter in the prescaler is 28,000. And in the counter period, I'm going to enter 1,000. So again, 280 megahertz divided by the prescaler divided by the counter period gives us the frequency of our timer. But keep in mind, there was always this plus 1, so I always subtract 1 in the prescaler and counter period to make sure we are precise. Other than that, we now have our timer frequency set up. We want to enable also our trigger, and our trigger is going to be the first trigger here, and we want to change that to update event. And that's pretty much it now. This is the most basic configuration for ADC, timer, and DMA. Now, Control S to save and auto-generate code. STM32Cube generated the structure of the project. If we expand out our project in the Project Explorer and go to drivers and then the HAL driver, and for example include or source, we can see the various drivers or HAL hardware abstraction layer drivers that ST has included. If I'm using a new peripheral to look at, for example, the peripheral drivers, the HALs, and see what functions are available. So for example, in the ADC, we can see we can get start DMA, conversion complete, callback, and various functions. And we also have this ADC EX, where we have various, for example, calibration functions, amongst others. And the calibration function is actually what we're going to use first. So I'll click on the function definition, copy that over, and go to main.c. Typically, I always want to calibrate my ADCs before I start using them. So after all this peripheral configuration in int main, I will place the calibration function. Then we have to figure out the arguments. The ADC handle type def depends on your situation, but in our case, it's HADC1 by reference. Our calibration mode, we can go back to the driver. We can see we have calibration offset or offset linearity. I'll just go with offset. And then we have single or differential mode, and I'll go with single-ended because we're just using single-ended in this design. And there we go. We want to do our calibration before we start our ADC. This is also mentioned in the function definition. You can see ADC must be disabled. Then after the calibration, we want to start our ADC with the DMA. Now, if we go back to the HAL ADC driver on the right-hand side, we can see there's a HAL ADC start DMA function, and let me copy that over. Quite nicely in this HAL, we can always see what the various arguments mean, at least in part. So copy that and pop that after the ADC calibration start. Now we have various arguments. We have, first of all, which ADC we want to use, and that's, of course, in this case, our first ADC. Then we have the data and the length. The data is a pointer to a buffer where the DMA places the converted measurements into memory. Length is a number of conversions. For this, let's create a global variable array of type uint16t, so an unsigned int with 16-bit width because we're doing 16-bit conversions. And we'll call that ADC data, and we'll just write in ADC num conversions, and then create a define at the top, and that to be 3, just to make it flexible for the application and we don't have these, so to speak, magic numbers. Therefore, we have our ADC buffer, which is a global variable in this case, which is passed to the DMA, and the DMA will keep filling every time the sample timer triggers and the conversions are complete. The DMA will keep filling this ADC data buffer. So therefore, we want to pass the data buffer, and we'll just cast that to the required data type for this function, and the length will be ADC num conversions. Now, although we've called this ADC start DMA function, remember we are actually triggering the ADC conversions using a timer. Therefore, we need to start the timer. And again, if you don't know the function, we can go to the HAL tim source file on the left-hand side and then see what function we have available. And what we actually want is the HAL tim base start. So I'll just copy that. So after the calibration, after we start the ADC with DMA, we will start the timer, and we used, for example, timer number 8. So this is all well and good because we set up the timer with a certain sampling frequency, sampling period. We will get periodic sampling conversions for our 3 channels, and the DMA will fill the ADC buffer 10 times a second. The question is then, of course, what do you do with that? What do you do with that data? And that, of course, depends on your application. But what I typically like to do, if I go to the ADC driver again, we can see there's this conversion complete and the conversion half complete callback. Now the conversion complete function or callback is defined weak, so we can override that, so to speak. So going back to main.c, I just copied the prototype. We can complete the callback function. So in here, for example, we could filter the data, we could convert it to a voltage, and so on. Now, if you know the reference voltage of your ADC, and that depends, of course, on the MCU you're using. In our case, the reference voltage is this VREF plus. Oftentimes that might be tied internally to VDDA. In our case, that's 3.3 volts. Now, of course, that 3.3 volts can fluctuate. Your regulator won't have an absolute 100% precision, so that might be off a bit. But for these non-critical cases, if we want to convert to a voltage, we just need to know the nominal reference voltage. In our case, that's 3.3 volts, but there are other ways of measuring this or deriving that, but that's for a future video. So to actually do a conversion between raw measurement to our voltage, all we have to do is take our reference voltage, divide that by the number of possible states depending on the number of bits of our ADC. So we have 16 bits, so we have 2 to the 16 possible states, and we subtract 1, and that gives us our conversion factor. So our raw ADC readings times this conversion factor will give us the voltage apparent at the ADC pin. For this very, very simple case, of course, depends on the scenario, depends on the reference voltage, which will of course fluctuate. But copying that over, we can create another define, for example, just very simply ADC raw to voltage that we calculated just now. We could, for example, create a floating point and we could call this pot voltage, also make this into an array of length 3 in this particular case, and we can convert the raw ADC data to voltages. What's oftentimes useful, especially with these interrupts, is that we actually make these variables and arrays volatile to avoid compiler optimization that might mess or try to optimize something out, which it shouldn't. So that's why we might want to add a volatile keyword. So therefore, just as a very simple example, in the ADC conversion complete callback, we could then loop through our conversion results from our raw data, and then simply say the pot voltage is our conversion factor times our raw ADC data. And this would be then enough to start with. I'm just going to put a short delay into the while loop, and then that's all I can build with a little hammer at the top left, and then we can upload this to our device. The way I'm programming this device is I have this tag connect solderless debug header, which connects to the serial wire debug lines, which we set up in Cube IDE to STM32H7. Then you simply have to create a debug configuration and click debug. So let me just do that now. So click debug. We can pretty much leave everything as default. I'm using an ST-Link v3 for this. Then click OK, and it'll compile and then upload via the ST-Link to the STM32H7 microcontroller. Then, once it's uploaded, simply click resume, and now our conversion should be running. So on the right-hand side, you can go to the live expressions panel, and then, for example, type in ADC data and enter. And as you can see here, these are the live expressions being retrieved via the ST-Link and the serial wire debug interface. And these are the raw readings from the ADC. And I have my 3 potentiometers. For example, the first one is now fully maxed out. That's ADC data 0. If I rotate that counterclockwise, you can see that goes down to 0, and I can rotate my potentiometer. Same with my second channel. I can rotate that counterclockwise or clockwise. That's ADC data 1. And then, of course, there's ADC data 2, which is my third potentiometer, which I can rotate, and that gives me different ADC readings. And this happens because of our conversion timer 10 times per second. But you can see, with no CPU intervention, we're doing nothing in this while loop. We are getting the data via DMA triggered on the conversion timer from our ADC. Then we can also type in, for example, pot voltage to see if the conversions are being done. And you can see here, our raw data is being converted to voltage. So if I turn my first potentiometer fully clockwise, we should get about 3.3 volts, which we're getting here. Second potentiometer, we can see we're getting the voltage out, and third potentiometer as well. As you can see here, we also have some bit of noise on these ADCs, and of course you could do that with more hardware filtering, and then also of course software filtering, for example. Now, all of this is great and works on most STM32 microcontrollers with exactly the same setup. However, if you're using the STM32H7 line of microcontrollers or any microcontroller that has, for example, data caches, there will be a problem when you're trying to use DMA. And this is regardless if you're using ADCs or whatever peripheral. The problem is with the cache, you have to do extra cache control when using DMAs. One way to get around that, for example, if you have these low speed requirements, such in this case where the ADC is just used for control settings, and we don't actually need the speeds of these caches, but we do want them enabled, for example, for other segments in our design, what we can do is place the DMA buffers we're using, for example, for this ADC in a different type of memory area, and make that memory area not cacheable. The way we can do that on STM32H7 microcontrollers is go back to Cube IDE in the system core, go to Cortex M7, and let's enable both the instruction and data caches, but also will enable the memory protection unit. So the caches give us typically quite a good speed boost, but cause problems when we're trying to use DMA and DMA buffers. And there are, of course, other ways around this, but for the simplest for this case, I found is to use the MPU, which is the memory protection unit. Then enable the MPU by going to background region, privilege accesses only, and MPU disabled during hard fault. Now we want to enable, for example, one of these memory protection unit regions. So I go on to the first one, just enable this, and we have various different options available, such as the region base address is important, the region size, and various access permissions, cacheable permissions, and so on. What we want to do is I'll change this to all accesses permitted, and I will disable all of the other permissions. And the important one for us is in particular this cacheable permission, which we want to disable for this particular memory region. Now the memory region will be some region in RAM. And for the H7 microcontrollers, they usually have a number of different memory regions in RAM. To see that, after we, for example, compile, we can go back to main.c and we have this memory regions analyzer, which is very useful. And we can see we have flash, we have various tightly coupled memories, RAM, RAM-CD, RAM-SRD. By default, all of our RAM variables are placed in the default RAM location, but we can also place them in these other locations using, for example, RAM-CD or RAM-SRD, and we can see the sizes here as well as the start addresses of those locations. What I'd like to use is RAM-SRD, and the start address is we can see here. and we have a size of 32 kilobytes. So we want our memory protection unit region to point to that address and that size. So region size we saw was 32 kilobytes, and the base address was this one here for this particular memory region. So then when we enable the MPU, that particular region of memory in RAM will be essentially protected, and we won't allow caching of that area, which will enable use of our DMAs. So if we save that to regenerate code, and if we were just to run this, we can still see that all of the RAM contents are placed in just this RAM section here and nothing in RAM SRD. And that's of course naturally because we haven't actually placed any of these variables in that particular RAM region. We simply enabled the MPU for that. But now we've also enabled the I and D caches. So if I now upload this to the board, just like so, we will see that actually we're not getting any of these DMA streams to work because these buffers are being cached and not refreshed and updated. So if I click on resume and then go back to the live expressions, open up the live expressions from before, we can see even though everything is running, because the DMA buffers are now being cached, as we've enabled them here, we're not getting any updates in our DMA buffers. Okay, so how do we fix that? Well, we've set up MPU config to make the RAM SRD region non-cacheable, but we need to place our memory, and in particular our DMA buffer, which is this ADC buffer, in that RAM SRD region. The way we do that is by going to the linker script on the left-hand side, so this, whatever your MCU name is, _flash.ld, and then we go down to the memory regions. And here we have these memory regions defined as before, and we want to create an attribute that places certain variables in this region. So the way I do that is then in the sections definition, we can just place this, for example, right at the bottom. I'll just paste this RAM modification in. So we're going to create effectively an attribute called .nocache aligned to 32 bits, and this is placed then in the RAM SRD section. I'll save that, go back to main.c, and now we need to add the attribute to this ADC data. Let me just paste this in. We use this attribute command with the section or with the name we defined with this .nocache. Then if I save and build this, we can see RAM SRD now has 6 bytes, which is 3 times uint16s, placed in RAM SRD. And RAM SRD was then covered by our memory protection unit, which we configured in CubeIDE. So now if I upload this to the board, because we've placed RAM SRD and our DMA buffer in this non-cacheable area, and click resume, go to live expressions, we can see our DMA buffers are working again, our DMA streams are working again. So if I rotate the potentiometers, we can see these are now being updated, despite having enabled the data caches. Now keep in mind, this method of doing this, of course, comes with the downside that we aren't getting this performance boost, but for something as simple as this, I think this is okay, and this is a fairly simple workaround compared to what you would have to do with invalidating caches and so on if you were to go a different route, but that's a topic for a future video. Finally, although this video has been mainly focused on the H7 series, I have also used this STM32U5 series, which at the time of making this video is a fairly new low power series by ST, and this has a bit of a different structure for the DMAs as well as for power domain setup. In CubeIDE, I have the project set up for this already, and I've gone through the usual ADC procedure. But if you go, for example, to DMA settings, we see that for this U5 line, we have these general purpose DMAs and also a low power DMA. So we don't actually have the DMA configuration directly within the peripheral section. So if I go to GPDMA, what we have is various freely configurable channels of the DMA here, which we have to configure a bit more ourselves. So for example, I enable channel 0 in standard request mode, and then I have to do the configuration for the ADC in channel 0 below. So we have to enable circular mode, we have to choose the right request, this is not done for us, and then we have various other configurations we need to do. In particular, source data and destination data aren't automatically filled out for us. For example, in the case of transferring from peripheral to memory, so from ADC to a memory location, our memory buffer, we have to make sure that our destination, in this case our memory, the destination address increment after transfer is enabled, because this is not automatically selected for us. So keep this in mind when you're using the U5 series, that you'll have to do more manual configuration because of these general purpose and low power DMAs. Other than that, the STM32U5 series also has some more advanced power control features. This is mentioned somewhere in the reference manual and also the data sheets, but what we have to do before we can enable certain peripherals such as USB or certain I/O banks, or for example the ADCs or DACs, is that we have to enable the power domains and disable the power domain isolation. The way we can do that is again either looking at the drivers. For example, for the U5, there's HAL power_EX, and we can see there's functions such as HAL enable VDDA, HAL enable VDDIO2, and VDD USB. Now, this is also in the reference manual page 411 for this particular microcontroller, the U585, where we have to set certain bits, and I've just done that manually, but of course you can just use the HAL driver. This effectively needs to be done before any peripheral initialization in those power domains that you want to use. Thank you very much for watching this video. I hope it was useful, and I hope it gave you some insight of how to configure the ADC with a sampling timer and DMA, and also the kind of quirks you might encounter when using H7s with their caching system, as well as U5 with this power domain isolation. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with embedded systems, PCB design, and firmware videos. Thanks again for watching, and I hope to see you in the next video. Bye bye.